Hello, we are Maximum Airtime Autogyro Designs, MAAD. We're a senior design team at the University of Texas at Arlington. And this year, we're presenting our entry into the UTA 3D printed aircraft competition, a fully 3D printed autogyro that reimagines how lift can be generated using additive manufacturing. The competition challenges teams to design aircraft powered for just 8 seconds to fly within a 300 by 160 by 60 foot volume, after which the aircraft must glide unpowered. Traditionally, this has led to fixed wing or parachute like designs. But MAD wanted to do something different. We designed an autogyro, a rotorcraft that generates lift using an unpowered, free-spinning rotor and a pusher propeller for thrust. Our goal is to advocate for a rule change in the fixed-wing category by proving that rotor-based designs are both viable and competitive. Our development followed a full engineering cycle, starting with concept sketches, CAD modeling, and aerodynamic and structural analysis. Each design iteration was informed by performance data and printability. The Ultimaker S5 was used to fabricate the fuselage and structural components, while the HP Jet Fusion 5000 provided high-resolution selective laser sintering printing for our rotor blades and parts requiring tight tolerances and smooth surface finishes. The electronics layout is modular and designed for ease of assembly and maintenance. Our autogyro integrates dual swashplate servos for pitch and roll, as seen here. A rudder servo for yaw, as seen here. And a pusher motor for thrust, as seen here. The fuselage and tail include press-fit slots, wire channels, and servo cavities to simplify the integration and assembly process. Design for manufacturing and assembly was applied throughout, allowing us to quickly assemble and test the system with minimal tools. Optimization was central to our design process. Using Altair Inspire, we minimize weight while preserving structural integrity, especially for our landing gear and rotor mounts. For the bearing system, we tested multiple 3D printed designs before landing on a unique solution, a custom bearing that used unprinted 3D printer filament as needle rollers. This design reduced friction, improved rotor spin-up, and repurposed standard filament as a structural component. Based on preliminary calculations and comparisons with previous aircraft, we estimated our autogyro would weigh approximately 1.5 pounds. After full manufacturing and assembly, the final aircraft weight came in at just 1.1 pounds, well below our projection. Aerodynamic analysis estimated drag to be around half of a pound during flight, and our selected propeller and motor combination uses approximately 1 pound of thrust. This gives us favorable conditions for our thrust-to-weight ratio and confirms the aircraft is capable of achieving lift and sustained flight within the competition's power and flight envelope. Our project demonstrates the potential for rotorcraft in a competition historically dominated by fixed-wing aircraft. By combining autorotation, modularity, and additive manufacturing, we created a competitive and innovative platform. We believe this design not only challenges the norm, but lays the groundwork for future rule expansion and increased creativity in aerospace education. We're continuing to refine our rotor blade geometry, integrate our custom bearing into the Swashplate, and perform full-scale flight testing as we prepare for our final report and competition. Thank you.